And I want to wrap up here. So when I go for a disk, I want to get the disk characteristics. And it's getting hard with all the different flavors of disks out there. Even on my home PC, when I went out and bought a disk drive, I had several factors to consider about what drive I wanted, including price and reliability. Okay? So the first thing is my controller interface. We've got SCSI and we've got fiber channel. Fiber channel costs more money. The fiber channel will basically allow more I/O operations on the bus at a time. So fiber channels are very common in your database market, for example. But SCSIs are cheaper. The other thing I'm interested in is the speed of the device. How fast is it spinning? What three speeds do we have these days?
54, 72, and 10.
Yep. So I go to Best Buy, or wherever, Circuit City or whatever, the 5400 RPM drives are down under $80 now, and the 10,000 RPM drives aren't in their store yet, but we can get them. Okay, so when I'm going to faster RPM, what am I getting? Go ahead, speak over.
Lower latency.
Exactly.
It's less time for it to spin around to find the next second.
So if I was delivering a video movie, latency probably will not help me. Bandwidth does. I may get bandwidth when my latency or when my rotational speed goes up, but my bandwidth will go up as well. But he was exactly right. Spinning faster is going to give me latency. I prefer to call this latency and seat time, but other people have it as rotational latency and seat latency. Latency being how long it takes. So the latency in this case, the seat time is how long it takes to get to the track. So that's driven by the mechanical head movement. And for example, if I have more cylinders or tracks on the platter, I may take more time to go across all of these cylinders. Okay, so that's what seat time is driven by. Latency then is driven by, once I'm on the track, how long does it take to get to the data once I'm placed over the track. So if I'm spinning faster, I can get to the data quicker. So in the database market, I'd much rather have higher latency drives. In the video market, I'd much rather have bandwidth. I may be able to get both. And that's where you get into a metric I call the crossover. Now, I'm the only person out here that talks crossover. I guess it dates my age. Crossover kind of went out the window for two reasons. Number one was zone bit drives. Zone bit drives have different bandwidths depending upon where you are on the drive. Okay. So in this example, crossover is seek plus latency times the bandwidth. Okay. So when I'm striping, and I put 4 drives together as a stripe group, is my seek and latency changing? No. It's the same mechanical drive. There's just 4 of them in parallel. Striping is raising my bandwidth, and therefore my crossover is going up as I stripe. Now, I said there are 2 reasons that crossover isn't really talked about by anybody, because with zone bit drives, I've got 7 different zones with 7 different speeds. Which one do I use? Anywhere from 5 megabytes to 12 megabytes on the older drives. The second reason people threw it out was because they derived the actual number and then used that number. That number isn't any good by itself. It's compared to the other drives out there. If every drive on my system is the identical same drive, they all have the same crossover. And I don't care about crossovers. But if I'm mixing drives, then I want to figure out the crossover of one drive compared to the crossover of a different drive. So in the older days, people would take the raw number that was computed here and use that to say, below the crossover, I'm latency driven, spending all my time with head movement, and above the crossover, it's bandwidth driven. So, for example, media base, delivering video. I may set up a real-time partition and make that a high crossover drive, and then use my low crossover drive for my data partition. In other words, you want to figure out, is this drive good at latency or is it good at bandwidth? And this is exactly what the marketing slides say. They say this drive is good for the video market and this drive is good for the database market. What they're saying is one has a high crossover and the other one has a low crossover. So I take the numbers, derive them, and then normalize them to each other. Simply say this one's low, this one's medium, this one's high, this one's really high. Okay? So the higher the crossover, the more bandwidth oriented I am. The lower the crossover, the more latency oriented I am. So when I mentioned this retrievalware application, the customer complained about performance. Analyst went out there, looked at it, and says, oh, you're doing 4K byte transfers, but you set this thing up 8 wide in a strike group. So he changed it, unbound the logical volumes, and rebound them 2 wide, which dropped the crossover down and turned a bandwidth drive into a latency drive. Now, he would have preferred to get them the right drive in the first place, but the drive was purchased based upon capacity, not what it's designed for. So to me, I'm going to come back to this quite a bit. Crossover is really important, telling me what is this drive good at compared to the other drives. So I derive the raw number and say this drive's got a low crossover. I'd like to use that where I need lots of little I/O. For example, a spam attack, bar spool MQ for sent mail. I'd rather have a low crossover drive there than a RAID 5. Because RAID 5 is raising my crossover. Now if I need recovery, I'd go RAID 01. But that costs more money, and that's why RAID 5 is popular, is because it's a compromise between price and performance. The RAID 01 will always perform better than RAID 5, but it costs you more money because it's twice the disk space. A higher RAID level has nothing to do with performance. What does the higher RAID level indicate? Less disk space for error recovery. RAID 01 is double the disk space. RAID 3 is more. RAID 5 is the least amount of space devoted to error recovery. That's really what it means. People go to RAID 5 thinking that that's a performance issue. It has nothing to do with performance. It has to do with how I create my redundant data. And this is where I talk about the lost RAID level. And some people call it RAID 10 now. But 01, where I'm JBOD mirroring rather than RAID 5. And that's what Disney needs to do. They need to get away from RAID 5 for their home directories. I hate RAID 5 on home directories.
RAID 5, the one that have one disk for the parity, right?
Well, RAID 5 is actually spinning the parity around all
Okay.
the
RAID
ladders.
3 is the one that's
All on one drive, right? And that's the geometry question I asked about earlier. How was my RAID cabinet put together? Okay.
How many disks in RAID 5 minimum?
4.
4 or 5?
4 plus 1, I
4
think.
plus 1, isn't it? That's
Yeah.
the minimum.
And that's the way they document it, that the parity bit is actually rotated along the platter, the spindles in the cabinet. But if I'm buying a RAID device, I want to know what this RAID device crossover is like. And when I'm striping, I'm raising the crossover, I'm raising the bandwidth, but I'm not helping my seeker latency. So if I'm in a database market where I'm doing lots of little I/O, I'd rather have a low crossover drive there and put the high crossover drives where I need bandwidth. So RAID 5 would be appropriate for a media-based video server, where all my video clips, which are large sequential I/O, are on a high crossover drive, but then all the inodes would be on a low crossover drive, because there are lots of little I/O. And that's why media-based gets into real-time partitions. So I can put my inodes on my data subvolume, and then put my large sequential I/O on the RAID 5 as my real-time subvolume. So whenever you're talking real-time, high crossovers. Real-time is designed to accomplish high crossover transfers. So anyways, that's a really conceptual issue. Is this drive good at database or is it good at video? That's the way the marketing people describe it. And I'm just using the word crossover to describe, if I've got 2 drives, how can I tell which one is better at which? So I take C plus latency times bandwidth, and then I can figure out whether it's a low crossover or a high crossover drive. I want to use low crossovers where I'm doing lots of little I/O. I want to use high crossovers where I'm doing large sequential I/O. And that's why I say too many people are overstriping, and particularly like on home directories. I'm sitting there writing "Hello Mom," Or I've got a 1,000 byte program, you know, in Unix, your C programs are broken up into small little pieces. And now I've got this wide strike file system, and I'm not taking advantage of it because the VI that I'm using doesn't do large sequential I/O. Too many people are using RAID 5s at home because of the redundancy capability and the cost factor. I don't have to double my disk space. But they're taking a performance penalty by running RAID 5. It's a compromise between price and performance. 0.1 will always run better, but it will cost you more because you need twice the disk space. So that's what I had to tell Disney. Go to RAID 0.1 and don't run 98% full. Quadruple the amount of disk space you have out there. That was my recommendation. And it took them a year of complaints before somebody came out and told them the same thing. So, I do care about capacity, but I also hate capacity. Drives are getting bigger and bigger. The trouble is there's more data on the drive now, which means more contention for the data. In the database market, I'd rather have lots of 4 gig drives than one 18 gig drive. Okay? Particularly in the compute server market. Now on my home PC, I've got a second drive there that's a 40 gig drive. That's just for video, and I'm the only person taking data off of that particular drive. Okay? So that's not so bad. But I'm saying I'd rather have lots of little drives with separate hardware paths to them than one big drive. And I go out to a site and they're I/O bound and they got one 40 gig drive. And everybody's contending on the hardware path to that one drive. So I'd rather have 4 9 gig drives than one 40 gig drive. So now I've got 4 separate hardware paths to push my data off. Okay? So capacity, we have to deal with nowadays. And that's going to come back to us. For example, externalizing logs. I went to Los Alamos and they put all their external logs on one drive. All it took was a sendmail attack, and now all that whole drive is busy handling all the sendmail inodes being created and destroyed, and now all the other file systems were throttling back because the log drive was busy. So when you start putting logs externally on a separate disk, the problem is, what do I do with the rest of the disk? You know, do I waste it? Do I put var80 and crash there? I certainly don't want to put home there or something like that. But that's the problem with getting larger drives. It's hard, and I advise minimum partitions per drive. I do not want to carve up a drive into lots of small pieces. Because now I got head movement as I go between the different partitions. Now on our workstations, we only have one drive. So when you use FX or XDCAM, it gives you the option of building it different ways. And one is to split root and user. Why do they do that? If it's the same drive, why do I want to split the drive in half and put root on one and user on the other?
So you can't fill up root as easily.
To isolate one file system from filling up another file system. If it was all /root, user people, home directories could fill up root. A sendmail spam attack could fill up var spool MQ. And all that would impact my root. And you don't want root to fill up. So getting these larger drives, I don't like to carve them up into lots of pieces. I'd rather have lots of headroom. And when you're talking performance, there's money behind it usually too. Which means leave lots of headroom on your file systems. We also talked a little bit about the geometry. I'll get into zone drives later. But how many sectors per track, how many tracks per cylinder, how many cylinders. FX gives me that information, as well as the technical specs. So I'm assuming everyone's seen some of these pictures, and I'm just wrapping up for the day here, showing what a disk drive is broken up into, and the fact that we've got it partitioned then with FX. In this example, partition 0 is a raw partition that's used for swap, or the database market. Why does the database market use raw partitions instead of using a file system? Let's see, I think we're all over 18. How many people have asked their parents to ask them to do their laundry for them? No guarantee it's going to get done. A database engine is not going to ask the kernel to keep track of its data. It does it internally. That's what's called the meta index. Meta means data pointing to data. So a database engine, rather than using the file system interface, which is user-friendly because you've got inodes and stuff like that, the database engine has a meta index and then does all of this I/O to a raw partition, because a raw partition is going to be your fastest. It's the least amount of code to get the I/O to the disk drive. And if I use the file system, now I've got to wait for the operating system to figure out to create the inode and to allocate it and all that sort of stuff. Oracle, Sybase, and Formex do it internally. That way they can't blame the operating system for problems. If they ask the operating system to give them something, there's no guarantee the operating system's going to respond the way they want. But if it's done within the application, then it's responsible for itself. So database engines have their own meta index and do raw I/O. Excuse me. We'll talk about logs a little bit later. I'd say it's time to call it a day. Print VTOC. Telling you what I've got for drives out on the system. There's also another command you can write down called dkmap. So dkmap is like a print VTOC to tell me how my file systems are laid out.
Do you have actually this switch drives? So that-
They got switched in 6.5,
Oh, okay.
primarily for RoboInst.
Oh, that's true.
Okay.
So that was the main reason they switched them. But at the same time, they did something smart because they moved the swap partition onto the bandwidth portion of the drive. So swapping is a bandwidth requirement, not a latency requirement. So now their roots are on the latency portion of the drive, and they're not wasting that for a bandwidth requirement. Well, let me come back to that. Anyways, to get my disk farm layout, print VTOC, dkmap, there's a couple other tools we'll talk about tomorrow. And I'm assuming everyone knows how the naming convention works. DK indicating it's a disk, S0 indicating SCSI 0, D1 indicating disk 1 on that SCSI 0, and then the partition names for the different partitions on that file system. And again, block devices are, everything is through file system buffer cache and has to be sectorized by the operating system. Whereas character interfaces like database engines can do 1 byte at a time. So database engines like to do character I/O because it's faster again. We'll get back into this, but there's 3 types of I/O. There's your buffer cache I/O. Everything by default goes through buffer cache. That's going to be your slowest bandwidth, but probably your best latency because the data's in memory. But to get to large amounts of data, I have to go through the operating system. That means a lot of instructions executed, which is going to slow down my bandwidth. Second type of I/O is called direct I/O, also referred to as raw I/O. This was a Cray SGI difference. The SGI world wasn't a Fortran environment very much, but in Fortran, direct I/O is also referred to as random I/O or record referencing I/O. So in Fortran, when you do a read or write, you say the record number you want to get to. And in the Fortran world, they call that direct I/O. But in the SGI world, direct I/O means we're bypassing buffer cache and doing I/O straight from user space, straight off to the file system. And Cray, we always called that raw I/O. And then the third one is character I/O. Now these two have to be sectorized. They have to be a sector size. Character I/O doesn't. And again, the SGI calls that raw I/O. Different than what Cray people always called raw I/O. So just got to be a little careful about that. This is going to be your fastest. Your best bandwidth. The latency would depend upon the drive. But there's the least amount of code involved in getting I/O done this way. This is just talking about the RAID levels, 0 being striping, 1 being mirroring. SGI does not support Hamming codes. And then level 3 is parity, and then level 5 is where I interleave my parity in my data. Zone bit drives I'll talk about when we come back to file systems. And in the workbook I just listed some of the drives that we've been using, the Scorpion and Barracuda drives. There's a lot of newer drives coming out, the TP3100s and stuff like that. I don't have the numbers on them, which is again the reason I'm getting rid of some of the stuff in this chapter, because it's hard to keep up. And then I also listed some of the older disk RAID cabinets that we had. This really shouldn't be the drive, but the controller, the type of SP controller that's in there, Phoenix controllers and K5 controllers, how they're configured with RAID 3 or 5 levels, and some of the characteristics about them. And then there's an FX label show all for the different drives, showing me my geometry questions and stuff. And lastly, there's just a couple of slides here showing me my channel comparisons. And everything we're using nowadays is really a PCI 64, which is about 266 megabytes per second on a PCI bus. Whereas SCSIs, we're typically at about 40 megabyte on a wide SCSI right now. But again, there's ATA SCSIs and newer clocks, faster clocks, and things like that going on as well. So it's just kind of giving you an idea of the bandwidth of these things. And then the last one here is for my home media. And I myself just got my cable modem about 3 weeks ago. Real nice. After 28A. Cable modem is right close to an Ethernet bandwidth from what I'm seeing. And it was actually cheaper than what I had before. So I don't have to pay for a second phone line and stuff.
But doesn't that wind up, the bandwidth wind up being really dependent on how many people are using it at the same time?
That's what I'm told, but I have not experienced it. And I don't want to go with DSL. A lot of people complain about DSL. It's not as fast as a cable modem.
As you get more users on it, they'll cut back your speed.
Yeah. It is a share. Eventually you do saturate, but there's more headroom on it than DSL. And for me, that's the most convenient and everything. I'm paying $45 a month, which includes the ISP service. So before I was paying like $22 a month for whichever, Prodigy or whatever, and then another $25 a month for the phone line. That was $45 right there. And now I get the same thing with better bandwidth.
I'm actually running wireless.
That'd be nice too.
My speed's not as fast as the cable modem, but it's decent.
Even these satellite, DSS satellite dishes and stuff that now have high bandwidth, at least for downloads versus uploads. But all I'm trying to do is show some of the different specs out there. And that's it. I'm just going to wrap for the day, but really it's HINV, topology or overview saying how it's put together, print VTalk to show me my disk layout, and FX label show all to show me specifics about the drive. So those would be my key hardware inventory commands. And the other one that I would add in here was DK map. Okay. So let's start up tomorrow morning. Now, first thing in the morning, I'm going to bring up the newer NQE and have the developer look at that problem. So I'm going to try to spend time, just lecturing during that interval. But I would like to run more codes. So before you leave today, if you can just fire off the 4 codes again, so we get more data. Okay? And then tomorrow we'll start going to the optimized version and seeing how we pilot and improve our clock times and stuff like that. So we'll see you tomorrow morning.
Bring up the newer NQE and let the developer see what's going wrong with it. Oops, it was on the proper route. I'd done a reboot, but I'll have to wait for it to finish. Come up that way. I still prefer it that way.
Huh?
I still wish I could do that.
Oh, use it.
Being able to write on slides, I can't write on.
That's true.
up the system, if it were new configuration, I'd be watching for any sort of diagnostic messages during boots and shutdowns, particularly since I have a job limit problem. I was just noticing this. Not so much the RPC one, but since I have a job limit problem, there's this thing going on.
Why did you find those error messages?
These are coming up on the operator console.
Oh, okay.
Now, the operator console is something that you can grab or you can direct somewhere. Some of it goes into syslog during the boot. But basically, this is standard out for the kernel. So whenever the kernel has a diagnostic, it may have a print statement, printf, within it. And all that printf statement's written into a dev special file that syslog is reading stuff out of. And it goes into syslog as well as gets directed into here. So I'm just looking at any sort of diagnostic messages during cleanup. You often get these kind of warnings depending upon the release that you're running. And remember I had mentioned that I'd done a K-Sync named D yesterday? And I can see it's kind of wrapping here, but PRF underscore LOCK is the duplicated block. And I'd have to look it up, but that's probably the profiling lock that's used by SSRun to check where the program is all the time. So there's a system call that does that. There's a lock going on within that particular kernel subroutine that checks on program stack information for a program that's running. So we're going to look at SSRun today. The other error message I saw, I myself not too concerned about this one here. But I did have this one, some XFS warning errors. I'm not sure what that is. I've never seen that before. Which one? Xlog find 0. It's a warning. So it looks like it's something in new 6510 that talks about cleaning up the logs during boot that I hadn't seen before.
There's a bunch of new stuff showed up in 659 too.
Well, I ran 659 a week ago and I hadn't noticed it, so I'm, just upgrading and looking for differences. So this is all the stuff that's coming into standard out to the operator console. There was a problem with /ptemp. I'm not worried about that right now, but we'll fix it. I'll explain why when we look at file system layouts. We haven't done that yet. So that particular file system, ptemp, is not mounting right now, but that's not a critical file system for me. I don't really care at this point. But here again is my get JLimit things when I'm starting up NQE. Now what's probably going on here is in my older releases, at the top of the NQE init script that starts up NQE, I've done a JLimit command to up open files and open processes. I'm just going to check that right now. And this is all the diagnostic stuff for NQE starting up. Everything looks okay there. Go to larger font here again. So I'm just looking for things that can get cleaned up. So if I cd ITC init.d, there's this NQE script that starts and stops NQE, like most of the other services. And it's calling this particular script to do the start, and then this one to do the stop. It appears when those are running, I'm getting those diagnostic messages like the one that I had. This is awesome. Like these right here. So I'm going to go into user Craysoft, NQE, and I should probably go into the ITC directory and grep for JLimit. And here's what I had in NQE init was a JLimit file, unlimited. Now that's a patch that a lot of sites are running
because their NQE doesn't support job limits yet. That's what this new version I'm going to try is about. So the way the sites were getting around it was NQE is starting up as root, and then all the jobs that spawns are keeping that same job ID. They're not getting new job IDs assigned yet because NQS doesn't know how to ask for a new job ID. So they're just upping the limits at a lot of sites. The file limit was the one that most sites were hitting. And again, what we saw yesterday was queues getting shut off, forks start failing because they're hitting these new job limits. Okay, so this is a common problem area that a lot of sites are going to be going through that deal with NQE or job limits in general. So right now I'm going to leave that there and ignore the warning messages. Let me just see if I do a JLimit command interactively here. The JLimit command is showing me what my job limit environment is like as much as the limit command did for per process. So per process I do have some limits, but on my whole job they're unlimited. And again, the JStat command gave me what my job ID was and everything. So here's the job ID. If I log out and log back in, the login command will give me a new job ID. Okay. POSIX calls it a session. There's a lot of similarities between sessions and jobs and QS requests. They're just different containers to group all my records together by. And we're also looking at JStat-AL to again show all the job limits. I'm logged in as root. And let me just try submitting a job here. JStat-AL. So look like it's showing it. Then run. Okay, the problem right now is it's pulling up a compiler path problem. That is a module problem that I've got. I've got my little list of problems here. That's something that I've got to put on there. Locked up. Is anyone else locked up?
Well, I just kicked off the back.
Okay,
I ran go.
that's fine. So we're going to have to wait. This is a situation where the event's bad enough where you can't look at anything. More than likely, we've probably got a swapping problem there. My window came back now. Let me just do a SAR. Take a look at the system real quick, see what's going on. So file system buffer cache and swap, we've got swapping going on. And that's what that initial event was. I'll talk about this a little bit later, but one of the key things in the operating system is something called the block transfer engine. We'll come back to this later, but real quickly, the block transfer engine is used to both create pages and also to move buffer cache buffers between user space and buffer cache. And if I get a burst of large processes, there are probably a couple of code 4s in there. Let's just bring up top and see what's running now. It's probably after the effect, but we had 3 code 4s that were actively visible there. One just died. But that instantaneous pause that I had there was the page creation for several code 4s at the same time. Now, page creation is single-threaded basically, so we can handle only one of them at a time. The block transfer engine is used to do that. It's a hardware piece of the hub or bedrock chip. So if I have a whole bunch of pages, and this is a 2 gig system, these were 500 meg apiece for them, so we had a burst of 2 gig of pages that we had to create rather quickly. And that tied up the block transfer engine such that my buffer cache interactively would also stall out.
Allocation overflow.
Huh?
Oh, you got a swap allocation overflow showing up there?
Yeah, one eventually died because I filled up everything that I could. And again, we've got virtual swap turned on right now, so that's the kernel saying I just killed something. Whereas before, it was the malloc and code 4 just dying on its own. And because I'm on the operator console, that's why I saw that. Okay. They'll also be in syslog. But I still have a couple of code 4s in there. By the way, with top, it's kind of messed up here. Let me clear and try it again now. So if I'm trying to do anything, I'm getting congestion on pages. They're going through buffer cache, and the block transfer engine is used to do that, but it's also busy creating the pages for these processes. There we just had another code 4 die. So again, what can I do? I can add more memory, I can add more swap. I've added as much virtual swap as I can. And we're probably hitting the allocated swap. In response to this, I guess what I would probably be looking at is gross view. And the SWP display. So we can find my terminal. I haven't tried X with this console window.
Well, it's better than the system, doesn't it?
Yeah, I couldn't figure out where to open. Let me go through my normal. Frankly, this is the only good display for what we're interested in right now. The SWP display will show that virtual memory map that we looked at yesterday. Now the jobs have all died. Here's the problem, by the way. I set virtual swap so big yesterday, I just threw a couple of zeros on it, that my entire display is showing virtual swap, and I have, this is my real system down here. Now that's the only disadvantage really to making virtual swap too big is this particular display. You drowned out the percentage of the display to all be pretend memory. So we can't look at that very good. So I'm in the process of tuning the system, so it might make sense to reconfigure that. Again, the swap-ln was showing that virtual swap as being 381 gig. So I'm going to go into git-c config, swap.options. I could have calculated it better. I'm just being, like I said yesterday, big extremes. So I'm just going to take a 0 off of that. Git-c init.p. Stop. We're going to come back to swap. Not enough space. We're not able to remove swap because of the code 4s that are still running in the system.
You want to kill him off?
No. That's fine. So there's 3 of them there. If I do my swap ln again, I hadn't noticed it before, but I've got a 256 meg swap, and 93 meg is what's left. So in the process, I wasn't able to remove this one because I was not able to remove that one. Had no place to move the 160 meg that's allocated out on swap at this point. Now we're going to come back to this later. I'm just responding to the situation.
So how you can are you trying to remove the virtual swap right now?
Yeah. But I was using the swap init script to stop everything and then restart everything. Okay, so in the process of running that, it gave me this, not enough space to remove my logical swap. Okay.
And you said that's
Because there were codes running, these code 4s are rather large in memory.
okay.
They're 1 gig apiece almost. We had 900 some meg. 400 meg was what we showed in physical memory. These are physical memory sizes, by the way. These are what we're going to talk about a little bit later called RSS sizes. We didn't get the virtual size. And remember yesterday when we were looking at memory, the command pmem, we never looked at yet. If I run pmem, I can find these code 4s now. And there's right now showing 787 meg. And at the top, that's all virtual data space for an array that has been reserved by malloc but not actually allocated yet. Nothing has actually referenced all of that. So each one of these, 787 meg of virtual space, and we're only using 490 meg that's in physical memory. Okay. And when you add it all up down here then, so we've got almost 2 gig of virtual and 990 of physical in the workload that's presently running.
How much we have in physical right now? 2 gig?
It's a 2 gig system, yeah, with
Okay.
HIMD. A little bit over 2 gig. 2 gig, 48 meg. And keep in mind, again, with pmem, that's only for running processes. We also had miser taking virtual memory, 1.5 gig. And we also possibly might have shared memory or interprocess communication resources that are reserved out of memory.
Now, when you got that problem here, that some of the process has been killed because there is no swap space, if you eliminate the virtual swap, it's gonna get even worse, right?
But the difference is, if I turn off virtual swap, the programs will fail on their own. So that if the program is properly coded, it could say, my malloc failed, let me go to sleep for a while and try again later. But it's the programmer's decision of what to do when there's not enough memory. And programmers have to realize that every computer has a finite memory capacity. So you always have to be prepared for a malloc failing. That's a reality of life. So with virtual swap on, the kernel did the kill, and then we see the error messages.
Now, when this process made the kill, it's because there is no more virtual swap.
There's
at
no
all.
more space to allocate. So the kernel resolves the deadlock by killing the largest things in memory. There's actually a couple of things in the algorithm, but how long it's been since it started, it will kill children before parents, and it will also pick on the largest memory processes first.
Because in this case, how much virtual memory did you put in the system?
We had 380, let's see, swap-ln again, 381 gig of virtual swap.
Oh, that's the amount that you're using, 288 meg? That number at
Right.
the bottom?
Well, no, that's the total swap-s type of number, if we looked at that one. Here's 16 meg that's allocated right now, 1.6 gig that's reserved, most of that is miser, and 1.6 gig bytes that were actually used, leaving us 382 meg available, and that's why those code 4s were dying, because they needed more than 382 meg, because they were, at a minimum, they were in the 400 meg with 700 meg, 800 meg virtual size.
Now that's 382 gigs available.
Oh, right. That included virtual swap, yeah. But these needed physical, I guess what I was trying to get to.
Okay, now that number at the bottom that says totals for the PMA that you did,
That one
I
there?
said no. Above that 288 over there.
Right.
That's the amount of memory being used right now.
That has been reserved by mallocs.
Okay.
So during our process, we have to first do a malloc, and that reserves the memory. Now on virtual memory paging systems, we defer the need for the actual memory until we actually need it and use it.
Okay.
So during the malloc, there's nothing done except a reservation made. Then when I actually do a read or write to the array that I'm processing or something, that's when I go to an allocation. And what we do is the TLB buffer says, I don't have this address in the TLB buffer, whether it's been created or not, I don't know. But the first time that I actually reference it, I'm going to get a TOB miss because it's never been referenced before. That's going to result in going to the kernel, and the kernel's going to look at the process and say, where is this page? Okay. So the program is sitting here with a virtual address. And this is something called ELF format to describe the binary for the program that describes the addressing scheme. And you have ELF formats on NT and other OSs, Linux as well. So in the program, it's a virtual address. We look at the TOB buffer and say it's not there, so we take a TOB miss. So the chip has a hardware event that causes an interrupt or a software exception into the kernel, and the kernel says, where's this page, where's this virtual address? So it looks it up in the page table. So every process on the system has a page table describing the pages in there. Now the first time it looks for that page, it says it's not there. So then we have to allocate and create the page. This is called a demand fill, a defill. And that's using that block transfer engine to actually create the page. It's hardware support to just create a B0, zero out a page the first time I create it. So I'm going from a reservation to an allocation when I actually do a reference of some sort to that particular page. The other way I may be referencing memory is a fetch, fetching instructions or something like that, and that would result in a TOB miss. And again, that piece of executable code might not be in memory yet. So we take a TOB miss, kernel looks it up and says, oh, it's out in /bin ls, brings it into the memory, and then we figure out where it is. Instead of creating the page, we bring it in what's called from the file system. PG file says that it came in from the file system, which means it was the executable text portion. Okay. So if it's a data piece, we create it with the block transfer engine. If it's the text executable portion of the program, we bring it in from the file system /bin or something like that and put it into memory. And in both cases then, within the page tables, we figure out what is the physical address that that page was placed or allocated in memory.
And what point it actually killed the process? When you tried to bring the...
When the physical memory, when this actually got large enough, when the allocations got large enough, we were hitting a physical memory allocation problem. If I add more physical swap, I'd be able to run more code forms. But then I'd have more swapping going on too. We'll come back to discussing how big the swap is going to be, but I said don't swap as a rule. Have enough swap there to run your workload. But don't be swapping all the time. There are some sites that swap all the time on their systems. So when you get into memory, there are a lot of different ways of looking at the memory counters. PS gives you pages, top gives you it in megabytes. This one is showing it in megabytes or gigabytes. This is showing the virtual address that was done by IRIX. So this was my virtual reservations. If I never really allocate them, they can exist out on virtual swap. But eventually, I fill up physical memory and my allocations start failing. And the kernel's running out of memory, so it resolves a deadlock situation by killing.
Now, here I only have like 130 megabyte of physical memory
that was being used by the processes, right?
Right, so I still have, because I have 2 gigabytes, so I don't understand how it killed.
This was after the kill. We don't know what it looked like the instantaneous time that the kill occurred. So these processes are sitting there doing malix, and eventually they hit that limit and they get killed. But by the time we looked at it, it was past. But we do have historical data so that we can look at that. We wanted to look at that. *r. And right in here, I can see where my swap ran out. I still had virtual swap memory available, but I ran out of physical memory and I ran out of physical swap, and that's the point where the kills started happening. This sample is occurring every minute.
So it means that even if you have virtual swap, if you're running out of physical memory.
Right, because the allocations were growing.
Right,
And
okay.
eventually I couldn't allocate anymore, which makes it, it's a commit. In NT, they call committing to the page. We reserve it and then we commit to it. So the allocation, I'm actually committing and creating a physical location for that page. And in this case, we ran out of physical memory. So when I ran PMEM, it was after the event. We'd actually had 3 of these code floors, I think, die. And by the way, the accounting data, I think it's a -F option. Let me just double check. Yep. The ACCOM command and some of the others have status with the -F option, so I can do -N code 4. And here were a couple of them that died. There's a couple more up here that died. The exit status is contained in the accounting data. The exit status is the signal number in this case, and if you look up in 11, you're going to find that to be a signal number that the kernel sent to kill these processes. So I'm going to do a man on signal and take a look at what an 11 is. If there's a 200 in there, it means it core dumped. Segmentation fault. Okay, so that's what the kernel did, was send a signal, segmentation fault signal to the process when it ran out of physical memory and physical swap. So it was trying to do an allocation. It was past the process of reservation, but the reservation wasn't really there.
If I do have in that case the swap, it probably won't kill the,
If I had more swap, I could run more of these. But with virtual swap on, I still get the kill.
right, but I mean swap, like, you know, like if I add like, you know, a file, you
Right.
know, a file
We've got
for
some
swap.
out there that I'm going to add today.
So in that case, the process won't be killed because they can't swap, right? Because
Right.
even they run out of physical memory, they can do the swapping with the
Correct.
file.
But even
whatever.
then, we still eventually fill up the swap too. So that's what we did in this case. Now I've got a whole bunch of other swap devices that we can add in here. And that will allow me to run more code 4s. If that's what I want to do. The disadvantage now is that I've got more I/O from my memory shortage problems. And if they're going to root or home disk drives, then I've got bottlenecks occurring when I start swapping. That's the problem with the workstation. I only got a single drive. When I start running out of memory, I start having the swap partition busy too. And I need that disk for other things. So you can get the swap traffic off of root, off of home, and put it in places that are isolated and get away with more swapping.
Dave, unless they've changed these machines, these have 2 drives in them.
Yeah, I realize that.
Okay.
In general, I was referring to workstations having a single drive system. The reason we have a second drive in these is to do striping and mirroring exercises.
And DMF.
Okay, but in normal, you still have root /dev/swap configured as my root partition that I'm swapping to.
What is it? Once you start physical swapping, your system performance is
Can degrade, it depends
101,
upon,
something like that. Like 100 times slower.
it all depends. If that's, you can get away with a lot of swapping if it's isolated down its own hardware path. And there are 2 types of swaps, swap outs and swap ins. It's the swap ins that matter to you. Because if I'm doing VI and part of VI is out on swap, or my data's out on swap, then I've got to bring it in. But there are a lot of times that you have data that gets pushed out to swap that you don't need. Okay, so there are 2 different stories there. But you can get away with it, but in the common environments, once you start swapping, it bottlenecks on your device, and then you can't get LS or bin or the shell, and things like that.
Yeah, but anytime you do a physical swap, you're going to see a performance hit.
To somebody,
Overall, it will impact. As a rule, it will impact.
it depends upon who's got pages out there. You know, you can actually time some of the stuff. So there's accounting data that says how long I waited for pages to come in from swap. But unfortunately, it's mixed with the I/O counters. Which, by the way, is why I run these workloads without the I/O on code 2 and 4, because I want to see I/O wait time show up when I know it doesn't do I/O. So anyways, I can add these swaps to a man on the swap command. And there's a -M option that says add anything that's in FS tab. So I'm going to do a swap -M. And now swap -LN shows that I've added more things in there. So I still am going to, in this case, the problem is I'm still going to swap the dev swap first. It's by priority. So I swap to 0 first, then I swap to my 1s, and I will round robin between those. Striping is probably not going to help you. Striping is for large requests. Okay. The size of these requests, pages coming in from swap are always going to be page size, 16 KB, no matter what you do with large pages or striping or anything like that. So striping is not going to help you get a page in any quicker. But it can help you get stuff out of memory quicker. We're going to come back to that when we talk about miser, but if somebody wanted to submit to miser now and memory was full of your code 4s, miser is allowed to take that memory away. So it's going to squeeze everything out of memory and push them out in the swap. That's why miser has the reservation when it boots. Okay. But again, the other way I could run more code 4s is turned off miser. If I decided I don't want to use miser, turn it off.
Can you tell me what's miser again?
Miser is a reservation system for CPU and memory. We're going to come back to it. It was kind of like a restaurant reservation system. NQE is going to talk to miser and say, I need a certain amount of memory for a certain amount of time, and then miser goes to a reservation schedule and schedules it.
Okay.
So it's just like calling a restaurant for a table.
So you can actually run without miser. The
Correct.
kernel will be intelligent enough to do the reservation
But
and schedule.
miser has the advantage of being guaranteed the CPU and the memories. And we're going to come back to that in CPU scheduling. So some sites are using miser because there's no variability in job runs. My weather model comes back the exact same timing every time I run it because there's no memory and there's no secondary cache effects in the program. So we're going to look for those sorts of effects. So I could have turned off miser if I had chosen not to use it. Miser is really for batch throughput with repeatable timings. You don't get system cache thrash effects with miser. We'll have to talk about miser on Thursday. So I added more physical swap here now too. In fact, I started off with the 256 meg swap. Now I added almost another gig in physical swap, which means I could run one more code 4. But I still, no matter what you do, have a limit to the number of code 4s that can run on the system. The other option that I had was to add more physical memory. I don't have money for that, so I'm not going to do that. I can't make code 4 smaller because that's the nature of code 4. So the last thing that I can really do to help in this area is look at job limits and drop interactive job limits down so that you cannot run a code 4 interactively. And then use NQS to prevent too many code 4s from running at a time. So I'm going to do that right now. I'm just going to do a queue manager and do a show global. And NQS says that its memory limit is unlimited. It says it's going to run as many jobs. I don't care what the memory demands are or what the memory available is. I'm just going to run up the load. Again, I've set up NQE to be wide open. So LSF and PBS have the same sort of concept. The syntax is different. I'm going to set the global memory limit. And going back to my other picture here, I did 2 gig plus another gig. I'm just going to pick maybe 4 or 6 gig as the maximum that the system can run. Now virtual memory was at 381 gig, but I'm not going to consider all that real. So I've got about a gig there, a little bit over a gig, 2 gig. So I'm overestimating, but I'm going to go with 5 gigabyte. Oops. as something that's realistic that I can run. Okay? Now I may end up upping it, I may end up dropping it a little bit, but I'm getting away from an unlimited because no matter what I do, my computers are limited to the amount of physical memory and physical swap I can put on the system. Now your question about sizing swap, the rule of thumb has been basically what I need for a dump. So they've been doing 512 meg or 1 gig on the big systems for crash purposes. That's the first rule. Maybe I should just write this down. So sizing your swap, which includes virtual swap. First rule is enough for a dump. And if you only have a single disk drive system, you need to save space for, your normal file systems. The second thing to consider is you need it bigger than miser. And that's something that we have not done here. By the way, you can delete everything. Swap can go to 0. You can get rid of all your swap devices. You can run without swap at all. But again, you're going to have tighter memory constraints. So if you are configuring your swap, if you've got a 64 gig system and you're going to have 60 gig that's going to be used just for miser, I advise you to have a 60 gig swap. The reason for that is that miser is making that reservation to start off with. If I load up memory with interactive users and miser comes along, miser is going to evacuate everybody in memory and it has to have someplace to push it. So that's why miser does the reservation from the start. Bigger than the miser reservation.
Where we can see what the reservation for miser.
Let me come back to that, but in config there's miser.options. So there's a config file that says when I boot miser, if you do a PS, I'm done with this global setting here, if I do a PS, EF, and grep for miser, oops, doesn't look like it's running right now. Let's just see here, swap-s. We do have 1.6 gig reserve. Oh, there it is. So right now it's asking for 1.5 gig of memory during the boot process, and that was determined in ITSI config, miser.options. So when miser started, it automatically reserved 1.5. So I would always try to have enough memory or enough swap for that miser reservation.
What's the C? Number of processors?
Yeah, number of CPUs. So I'm asking for 12 CPUs, but I don't reserve those. Whereas the memory, there was a reservation during boot. Okay. So I've added more virtual swap, I've added more physical swap. I dropped down virtual swap a little bit, and I also dropped down my global limits so that NQE doesn't try to run too much stuff. Because no matter what I do, I can run more code 4s than there's capacity in any system out there. As big as you can build the system, I can fire off 1,000 code 4s and fill up the system. The third thing I was going to say, if you make it too big, then swapping is going to be a problem. You'll have high swap rates. Older sites used to set their swap to like 20 times more than their physical memory. So they'd say we'd run 20 times more work than I physically have on my system. And this is a customer expectation issue that has to change. Because that was done on crays that were single CPU with different architectures, completely different systems. And they were designed to be oversubscribed because there was a memory scheduler that could decide who swapped and who didn't. So on a Unicode machine, we could swap the entire process out during the day. Bad for that process, good for everyone else. Because everyone else had the real memory. So if I make swap too big, then swapping is going to be a problem. So as I add more and more swapping and I overload the system, I'm going to have more swap traffic, and that's going to congest my system more.
So, but in that case, then the only solution you have is to have more physical memory, right?
Right. Or back off on the workload. or fix the application so it's not too big. Okay, so I had an order there, fix the application first. Maybe somebody oversized the table, and it was a one-time event. They should have fixed the program first rather than going out and buying more memory, the Oracle story. So those are kind of your rules of thumbs. There's a ratio issue here. I like to keep the ratio less than 5. Older standards, it was actually at some sites 20-1. So I go to NASA Marshall down in Huntsville, Alabama, and they're still running a IRIX machine 20-1, and 20 times more workload demand than they physically have on their system, and their swap is 20 times bigger than physical memory. Now, if you maintain that ratio, 20 times the workload to physical memory, and physical memory is going into the gigabytes and higher, you can't maintain that ratio forever. Pretty soon your entire file system is swap or something. So I believe in not swapping and trying to reset customer expectations to say that just enough swap to breathe and give you what you need to survive, but don't just keep adding swap to the problem. Physical memory would be better. So I'm just responding to those code 4s that got sent off on the system. Let's see. At this point, I need to get NQE started and get the developer working, looking at it. So QStat, I have 33015 running right now, so I'm going to shut down NQE. Were those jobs done?
Code 2s are running, that's all.
Okay. I'm going to do a shutdown anyways. I like to test checkpoint restart. That's one other advantage of the batch interfaces is that if you get a system interruption, there is a recovery image called a checkpoint or restart image that allows me to not lose work. I've got sites that run Gaussian in the background for months, and they don't want to lose their data 2 months into the computation or something.
Did you ever use CView?
Use with what?
CView?
CView? No.
C-V-I-E-W. That's
No.
the checkpoint
Oh,
restarter.
yeah, there's CPR man page and stuff, yeah.
Yeah.
Now NQE is doing it automatically. That's for the interactive environment.
But it works pretty good.
Yeah.
It's impressive.
So anyways, I'm just going to check.
So over there, which one told you what is the number of jobs that's
I saw right here, 5 total running.
Okay.
They were running right here in this
2, 3,
column.
4. Yeah, there's 5 of them running.
Okay. I could have done a QStat-A as well.
When you talk about batch, you know, what exactly that means?
That means that I don't have it tied to a terminal. There's no human processing. It's done in the background.
Okay.
So cron events, @command, the background sign, ampersand sign, those are bash type of command runs too, but they're not resource managed.
Right. Like actually immediately, right?
Right.
Immediately running in the background all the time.
Right.
Exactly. Okay.
But they would call that more of a daemon than a batch process.
Oh.
But if I, for example, had file system backups, I may be doing them at or cron or the batch command itself. But those are just done by time, whereas the NQE, PBS, or LSF batch interfaces started off based upon how much they're asking for and how much is available after reservations. So it prevents me from overcommitting the machine. So there are 3 batch interfaces, and then there are all the different standard Unix batch interfaces, the ampersand sign, batch, cron, the BG command to fire something into the background, the foreground. Those are batch concepts, but none of them have load control to them. In those cases, the job could die. And that's why I was dropping down my memory limits here to try to get reliable code 4s. And NQE was saying, I got unlimited memory, so it just kept firing off code 4s. Now I've dropped it down to 5 gigs, so it's never going to try to run more than 5 code 4s. And that may still be too high, but I'm just narrowing down to the region that I want to keep. So I start off real big, not going real small, and maybe I might up it or down from this point. So I'm going for a big swing and then trying to narrow it down from there.